tool is in relationship to the part, right? So let's say you want, this is the part we're going to cut. By the way, it's a bit sharp, so be careful, don't put your finger on it, and don't use it as a knife because it will cut you. So the biggest challenge we have is to make sure that we program a part, and we know the geometry of the part, and we want to make sure that the machine controller, computer numerically controlled machine tool controller, CNC controller, this is a computer with some additional features, you know, like controlling drives and so on, knows where this part is in the machine area, which is a vice on the table. So this machine has 3 axes of control, X, Y, and Z. The Z is the vertical axis, so whenever we hit minus Z, we will see the Z values here. So this is Z000, which is the home location. So whenever you see Z minus, it means that we are actually cutting metal, or whatever we are cutting, plastic. Okay, so the challenge is to make sure that the tool center point, I'll show it on the drill because it's easy to see. The tool center point, which is like this, is known to the controller, and then it's part of your geometry. So when you are drilling a hole, we are drilling these holes. We're not drilling this hole, not this one.
That one, yeah.
We are drilling these holes. Bless you. Then, well, sort of. These are not the same thing.
You knew that.
That's fine. I don't have 2 of those colors.
Sure, that's fine. So, when we are drilling these holes, you don't want to bang and hit the surface, right? You want to go rapid, a couple of millimeters. Usually it's 2 millimeters, roughly 1/10 of a cell, top of the surface, and then you go very slowly, and then you will see that we have this what we call packing cycle. So we go in and out. That's a built-in cycle. So we have the controller's help in that to make sure that we don't have to program every little motion like that. So the next problem then, of course, is to make sure that not just the tool tip is known to the machine in relationship to the part, but also the part coordinate system is known to the machine's coordinate system in relationship to the machine coordinate system. So you basically have the tool coordinate system, you have the part coordinate system, and you have the machine coordinate system. And you have to align the 3. The tool coordinate system is relatively simple because it's usually 1 axis only, plus a diameter maybe, right? But the part and the machine is typically at least 2, maybe 3 axes, 2 axes on a blade, X and Z. On this machine is 3 axes, X, Y, and Z. And sometimes we have, in the video, you have seen 5, 6, 7 axes of control as well. So you can have many, many axes of control that you have to line. So what we're going to do first is I'm going to ask Gregory to show us how we set up a tool, because it's very important for the operator to make sure that the length of his tool tip, is known to the computer. And of course, when you put a drill in here and then tighten it, you can have a little play here. You can set it in different ways, and you don't want that because you want it properly above the surface. You don't want to hit the surface too fast, right? So you need to know this distance, and it's called the tool setup. We also have an opportunity here to do tool length compensation. So in other words, we can make sure that we add values or distract values of the tool, so we can make it longer or shorter as the computer sees that, right? So let's see how that is done first.
That's my Z home position, so I have to tell it the length of the tool. The length of the tool is from the back of that flange to that tip. So for each tool, you have different length, because they all vary, as you can see there. So to do that, you bring the vise underneath the tool, and you come down with your manual.
That is called jogging. That's the jogging wheel. You can set the step sizes. You can see the Z is moving.
So this is 1,000 1/10, I mean 1,000, 10,000s, and 100,000s.
It's in inches, yeah. You can set these controls for metric or imperial.
Freedom units.
So I come down in 1,000 increments. This is called shim stock. This is like 2,000 thick. So I come down in Z until I get drag on the shim stock. When I have drag, I know I'm only 2,000ths away from the part. So I go to my offset page, I hit tool offset measurement, and whatever number is there gets dumped into the memory. And I do that for each tool, so now the machine knows the length of each tool. If you didn't do that, the machine would just try to machine the part up in the air like that. The spindle would just spin, you wouldn't know where the top of the part is.
Okay, so again, it's very important for this machine to know where things are because it has no eyes and no ears, and you don't want to go too fast into something that you don't want to break into, right? So the other thing that you should notice is that these tools are very special and also very precise. This is called the ISO 40 shank, which is a tool shank. It is a precise way of making sure that the tool is aligned so it doesn't wobble. We have this, sometimes they call this the mushroom. So the machine has a very strong a hydraulic, sometimes pneumatic, but this is hydraulic device that will pull this in, and the center of the tool is maintained therefore. It also has these slots here, so the torque is actually transferred on these. So once it is in location, mechanical springs hold this, not the pneumatics or the hydraulics, because of why? What do you think? Well, it's very important. What if you lose hydraulic power? Let's say you're pulling this with hydraulics and holding it with hydraulics. What if you lose hydraulic power?
Yeah.
Tool will drop, right? Is that dangerous?
Yes.
Very good. So you have a tool rotating at 3,000 RPM, flying all over the place, right? You don't want this to be flying out as bullets in this, even in this lab, right? Imagine a big shop with lots of different machines. So the actual way they hold it is spring-loaded, mechanical spring-loaded, which is very, very unlikely to break. I mean, the probability of that is something like the moon and the earth crashing. So the beauty then is that you transfer the torque, you have these slots, and we transfer the torque. So we're measuring the distance of the tool tip from this surface to this, and every tool is different. But the shanks are the same. This is also used by the tool changer. We're going to see the tool changer. On this machine we have 10 tools in the tool changer. As you've seen in the videos, we sometimes use even 120 or even 240 or more tools in a tool magazine, and we change that automatically. A tool change on a machine like this is around 5 seconds. Human operator, what is a really good time for a human operator changing tools? 5 minutes? I would have said 2 minutes.
Oh, you mean manually?
Yeah, manually, yeah.
Yeah, probably about 30 seconds or so.
30 seconds to a minute. So, you know, already 5 seconds is a lot faster than that. On more extensive machines where time is even more important, sometimes you can see tool changes within 2 seconds. So you see when you look at this for a whole year, adds up to productivity. You know, you're saving days and days on just tool changing. You know? And you're talking about $3 million machine, then that's a lot of money, right? Because you didn't buy the machine for changing tools. You bought the machine for making parts, right? Because this is where your money is coming back from. Okay, so